today's Energy Central webcast entitled Edge-Powered Grid Excellence, Streamlining Operations and Unlocking Insights. A few housekeeping notes we'd like to mention. We acknowledge that given the higher demand on internet connections, where many are working from home, the technical issues you might experience may be more pronounced. If for any reason we find the need to restart the event, we invite you to click the same link to rejoin us again. If you cannot get adequate sound from your computer speakers, you may dial into the audio portion using the telephone number listed in the right-hand panel of your interface under the audio section. We invite you also to submit questions at any time using the interface on your screen. I'm thrilled to introduce today's keynote speaker, Michael Oshetsky, Micatu's Chief Technology Officer and founder. Micatu's passion is to fundamentally change the way the world manages the grid using light with solutions that transform operational awareness for the power and industrial industries. As a founder of Micatu, Michael has helped build the first company to commercialize the next-gen optical sensing, and Micatu's innovative technology enables decarbonization of the power grid and provides real-time information for predictive and reactive information. With over 20 years experience in the optical industry, Michael is considered an expert in the field of optics and sensing by his peers. His drive for innovation has resulted in numerous patents in the energy, optical, and data processing fields. With that, Michael, welcome to the event. You have the floor.
Thank you. Thanks. It's exciting to be back. I think this is going to be a great conversation today. And I think we're going to change it up just a little bit when we did from the last webinar. Please feel free to put questions in while we're going through the material, and we'll stop at the end of the presentation here to go through more questions, but feel free. But really what we're going to focus today is, where are utilities heading? What are some of the challenges, and what are the focus areas that utilities are really going towards? Our company provides next generation optical sensing, and we're really seeing how we can do much more with the data and processing data on the edge. So I'll talk about those topics today. Also talk about some topologies of how we see and what we see the trends of the market going towards for edge data processing, integration of AI, cloud data, and how that ties back to central controls with AMI systems. But the three key things that really our focus is right now in the industry is sustainability. I think we all feel the pressure towards going towards a carbon-free society, and there's many challenges to get there. Not only the fact is that it's been legislated to move in 2030, 2050, depending what state you're in, but also the move towards electric cars. I see it in the news every day that you see more and more manufacturers are going 100% electric. It's exciting, but also it brings its challenges. So we're going to talk about the sustainability and what that looks like and how that ties in. But there's another big thing too, is affordability. And affordability comes from as more and more carbon-free transportation comes online, it really puts a strain on the infrastructure, on the distribution side, on the transmission side. And as the neighborhoods, for example, let's say my neighborhood has more and more electric cars, that infrastructure has to grow, and that infrastructure costs money. So we're going to talk a little bit about how can we maximize capacity while minimizing some of these investments, because it's going to cost quite a bit of money to grow this. We're going to talk about that. And I think the last thing is how resilient is the grid. It's a very important topic as far as mitigation of wildfires, stability of the grid. As more and more DER and renewable energies come online, we really have to think about how can we maintain and ensure stability of the grid and resiliency. So exciting topics today. We'll go through this, and feel free to ask any questions as we go through. So this is an exciting slide, because when I look at this, I really see that we are in a fundamental transition of the power grid. We're going from fossil-based fuels to fully renewables, right? And of this, if you can see how much of a gap that we have from where we are from today to where we need to go. And it's going to be focused around these powers of renewable energy with solar, wind, hydrocarbon, nuclear, hydrogen-based. I think as we progress forward, this need and gap gets larger and larger. So the questions coming is, how does this fundamentally change the grid, and what is driving some of these topology changes, and what will this topology look like as we put more of these energy sources in? It's staggering to really think that 200 gigawatts is needed by 2050. I mean, 2,000, excuse me, gigawatts needed by 2050. So as we move and fundamentally transform our sources of power, the topology has to change, but not only the topology, our interaction with the grid. We're all turning into what I like to say is prosumers, right? Prosumers of energy. Not only do we generate, now we consume, now we share. And I think our whole concept of the power grid, from the way it was a linear topology to the circular, is also evolving, not only on a technology base, not only on a where the actual power is generated, but you as actual consumer. So it's pretty exciting. But also with this renewable, as we go forward with this, there's going to be required quite a bit of storage. I think the good thing with storage is that a lot of electric cars have a ton of storage. So this gap in storage, that we need 930 gigawatt hours of storage by 2050, is going to be a problem. I think it's a massive problem, but I think there's solutions out there for it. If we're moving from a carbon-based cars and transportation to these EVs that have storage, so bidirectional management and DER on the consumer side is growing massively. If we look at some of those numbers here, you can see the DER market's huge, right? And where is it heading, right? And by 2027, it's nearly tripling the size of where we're at today. So it's exciting to see this, but also in the back of our heads, we have to think about what does this mean for us as we move through it. So I got a question popped up, and let me see. The environmental implications of such a huge share of wind and solar and other fossil fuels are still not clear. You know, I agree with that. This question just popped up in my chat here. It's not clear what the environmental impact will be. Now, I think if we're looking at the technology we have at this moment, I think that they're playing a big role. But as we know, there's other technologies always in the wayside they're developing. And by 2050, which is, you know, it's about 30 years plus from now, it's we can see what technologies come in. So good question. So looking back at this, looking at the solar side and how much actual distributed energy resources we're going to put in there, you can see that that's moving forward at a great rate, but you can also see that the EV charging infrastructure, this is driving a lot of that first point I brought out, was that the cost to put in this infrastructure when we have so many charges that need to go into each distribution feeder network into each neighbor and residential neighborhood is something that's really growing massively. So the question comes back is who shares that cost? Do all rate users share that? Do we have to incentivize people that actually have electric cars to help cover some of this cost? Those are some of the questions coming up. And I think that really drives us towards the technology side and how the topology of the grid is going to change to actually match that. So let's talk about that a little bit more. You know, I call this grid modernization, but I've shown this in a couple other talks, and I've really looked into this, is that what does this circular topology look like, right? What does this look like on an interaction from a consumer base, but also from an operational base? And let's say if you're a microgrid, you're a utility operator, what does this really look like? So let's just go through this and we can kind of talk about each component of this. Really where the grid's heading is that it's going to be a bi-directional microgrid that's tied into many microgrids and larger grids, right? We're heading that way because we have utilities that actually have wind farms, solar tied in, right? That's connected to different components of the feeder in different components of the actual substation feeders, and how do we tie that in? We have large scale solar. Now, you might have a Tesla power wall at your house. We have to tie that in, and the storage. So there's opportunities for that to actually produce and be able to supply, depending on how we actually tie that DER into the grid, right? We have campus microgrids, we have industrial microgrids. Those are becoming much more popular because as part of this drive towards carbon-free, also we have to be carbon-free on a campus, on an industrial facility. So renewables on a localized level into an even smaller microgrid tied into a microgrid is interesting. So the other interesting things you'll see too is that there's back to the residential side, right? Is it's becoming more and more popular of measuring the actual desegregation of your meter. So AI and technologies to the point now where you can actually desegregate your load profiles. And so digital twins and digital models are becoming much more important because we have device level control of your actual energy consumption. So the big question I see in a lot of the industry trade shows and talks we go to is consumer participation, right? Consumer participation is something that's it's a curious thing. And the reason I say that is that you as a consumer have the option to opt into these programs. So that, for example, let's say the utility has to do load control, load shedding. You come home from work, you plug in your electrical car, and all you really care about is getting that charged by the next morning to 80%. So you can get back to work and have some surplus capacity to do whatever you have to do. But that participation means that the utility gets to choose when they charge it, as long as it gets to 80% the next morning. So some people, I think some technologies and some companies, that's a participation into this. Actually, we're going to have to consider. Now, same is true with your washer, dryer, electric hot water heater. I know in New York State, they're moving more and more away from gas, natural gas. So these electrical appliances come more online. You know, I think it's important to have participation, but how do we drive participation, right? Do we legislate it? Do we incentivize it? Is it a combination of both? It's something that's a challenge we're gonna have to go through. But if you really look at the top 5 challenges that I'm seeing, and there's probably many more, is to put a microgrid of this scale together and to tie fractal microgrids together. It really takes real-time situational awareness and reaction. Later in the presentation today, I'll be talking to you guys about not only operational topologies, but the importance of latency and latency response times in these topologies, right? I see this quite a bit. The next point is data. Data is very important, but high value data. You know, I think each device that we at Micatu, we can generate gigabytes of data a day. And of that, which part of that data is important to the utility? So not only is data algorithms for ensuring that we have high value data, but also reducing bandwidth such that the value of the bandwidth of data we actually transmit is of value, right? I think DERMS network edge control is another thing. So we're going to talk about this more in detail, and I talked about it in my last talk, which was in July, is that as we move more towards the edge, what are the DERM devices? What are the switches options, and how can we actually do load management? How can we actually tie it back into demand response and stability, right? The other exciting thing is 80% growth in consumer distributed energy resources. That's a huge growth sector. It's on the consumer side, so it's on the other side of the meter. And last question I brought up before is who pays the cost? This is a change not only into topology, but the equipment and resources required to do this. So moving on here. So one of the things that I find really interesting, and when I think about grid edge and when I think about circular topology, I'm thinking a lot about virtualization and virtualization of power also. What really we're heading towards in some of the data by having high fidelity grid edge data and grid edge processing, it gives us the opportunity really to get into virtualization of power plants. So what do I mean by virtualization of power plants is that you have smart thermostats. You can now control load, right? You have rooftop solar, so we can actually activate that. And all this goes together with your electric car, your power storage, your appliances, your office. All these options here can be aggregated into a DERMS aggregator, and we can actually treat that as a virtual power plant. It's that virtualization of the inertia, right? So, for example, through the advancement in the edge operation, it really gives us the power to manage load in a very fast way. And when I say in a fast way is that during peaks, during higher demands, during surges, during other components, versus trying to virtually spin up a power source as we're doing this with our actual operation on the edge side. Well, this is going to become much more prevalent in the grid of the future because it has to be, right? If we're going to this bidirectional and going for actual more and more energy production and consumption control, this is a vital part of it, because what this does is this allows us to have capacity increase without actually having that massive infrastructure build out, and it kind of buys us some of that time as we build this out together. So it's interesting. So how does this look a little bit more on the operational side is that I put together a diagram here that really kind of explains, and it goes on this from the operational sensing side, from the distribution, sub-transmission, and transmission side into what we call the digital twins or digital clones. As part of this is modeling and forecasting is becoming much more prevalent, and the application of AI into this. So with digital clones tied into a topology where we actually have the information on the edge and process it on the edge, enables us to have much higher predictability, not only of current state, but next state, energy buy, what's going to be the actual demand for tomorrow, 24 advance, 48 hours in advance. That's really where we're seeing this head. So just to kind of walk us around what this diagram looks like and what it means is that as the grid edge, really what we're seeing here is by putting advanced sensing on the grid edge, where we have high fidelity voltage, current, phase angle, power factor, it really gives us the opportunity not only to understand the current condition, do fault analysis and prediction, but also the DER control. So many devices, and I'll talk about it in a little bit later slide here, it gives us the ability now to start looking into this topology where we can start to virtualize these power plants. This is tied into a digital cloud asset. So by going into a cloud asset, it really gives us the capability not only to confederate information, have federation of learning sensor into AI, but also gives us the ability to locally process data on the edge and actually transfer that high value data. Likewise, it's sent to the ADMS or even management system through any of these SCADA or different communication protocols, which we'll talk more about. But what we're seeing is that you can have rapid response on pre-programmed or pre-learned actual events that can either autonomously happen or can be overarchingly supported by the ADMS or the actual operators of the utility microgrid, whatever the situation is. That tied back with the actual cloud gives us the ability to then have digital clones, digital assets. So not only do you have an operational edge model, you also have a very strong predictive model of your current topology and what your energy needs are. So with that said, let's go on to the next slide here. And we're going to talk a little bit more about what are these requirements on attributes from sensing from the actual requirement and how's that tie into the sensing. Really what we've seen at Micatu is that traditional measurement devices, while they've served a really good purpose of providing voltage and current, there's a lot more to this grid of the future. There's a lot more than just having a sensor. I think really what we've been focused on, what we see is that, the utility requirements of revenue grade measurement, now that we have bidirectional flow of energy, voltage regulation and protection, right? VVR, and that's a big component going forward as we have to lower our voltage so we can increase capacities, right? Without that massive capital spend. So to do that, highly accurate and highly precise sensors, they've been out there, they've served that purpose, but really what we have to do is move it to the next level of information. We've all seen this phenomenal progression in AI, particularly around ChatGPT, Elon Musk's company, around it's incredible of the information that we have and the information that we can actually interpret now with these large language models and the predictability and the accuracy of that. So, so one of the things that's also interesting is the DER awareness, right? So as we put more DER on the grid, it really comes back to tying in the harmonics and the harmonic component. As we go from solar and renewables, typically DC, and it's DC to AC, that inversion, can cause a lot of issues. Also, the load profile is changing on the grid also. As we move more and more towards LEDs, our computers, all these nonlinear power sources really cause havoc. And a great insight to this is going to be harmonics as we go forward. And we're not talking about the harmonics on 9th and 10th, we're talking up to the 250th, to the 2000s, hyper harmonics. So that is part of this DER awareness, but also ensuring that resilient grid that we spoke about earlier. There's going to have to be mass deployment of overhead and underground sensing, right? We have a large, 6.3 million miles of distribution grid. So there's going to be a lot of sensing, but the sensing and informational tieback has to be modular. It has to be retrofittable to your existing cat bank controllers, your switches, but it also has to be future proofing where it can have that data and edge awareness. So I'm going to pause for 1 second here, and I got 2 interesting questions. So the first question is, what do utilities need to do to have these grid edge capabilities, the costs and actual benefits? That's a great question. And I think what do they actually have to do is that it's going to be a phased process, right? First off, you have to have actionable intelligence to start putting this together. There's many companies, and we've have some great partners in the industry that have solutions that actually are cloud-based. And the actual benefit for this is there's 4 primary ones, right? We talked about it earlier, is that resiliency of the power grid. To be able to detect faults prior to their happening is a massive value, but also to be able to isolate and control faults faster is obviously a major priority for certain utilities. Second one is that volt VAR is a huge opportunity. We've all talked about it. There's been successful deployments of that, but that needs to get massively scaled up. So if you can provide actually a reduction in your volt VAR and energy consumption while not having to increase capacity, there's a huge benefits into that. And also there's asset management. I know one question just came up, said, is vegetation management a part of this digital approach? Absolutely. That goes back to the resilience of this, is that when we're looking at grid edge and we're looking at vegetation management, limbs hitting distribution lines and having phase-to-phase faults or phase-to-ground faults are not a good thing. So that's part of the resiliency for this. So if you're a grid operator, you're a utility, you're on the distribution side, and you're looking to say, what's the benefit to me? Operational insight and situational awareness is a huge benefit to this. Really where we see this going, we'll talk about this a little bit more in later slides here, is that predictive analytics and predictive is actually, we'll be able to identify faults before they happen. We'll be able to prescribe what the issue is, and we'll actually be able to prescribe when we can have to actually send out service crews to make that happen. That's a powerful statement, but with the AI, the technology, that's really where we're heading. So exciting stuff here. So let's get back to this and we can go forward here. So response to situational awareness, that's huge. Situational awareness to know what your grid's doing, how is it doing it, and as we go more bidirectional power flow, we got to know. So, and then the most important is safer for crews and customers, right? Wildfire mitigation, understanding that how can we make the grid safer? We can't have major impacts to our customers. We can't have major impacts to the operators. So we actually have to have sensing that's safe, but also data that enables us to understand that faster. So when you tie this together, and what are some of the devices on the new edge of the grid, is that I've really tied this together. What are these ID devices, and what can we do with these to help actually control some of the different parameters? We have IEDs, we have PMUs, and sorry, I'm gonna go through all these different acronyms, and many of you guys know what they are, but they're actually on the presentation here. RTUs, we actually have WAMSs, AMI, data acquisition, SCADA, DNP. So there's going to be a combination of the solutions that we're going to have to retrofit this equipment. There's quite a bit of cat bank controllers. There's quite a bit of different pieces of equipment out there that actually have to be retrofittable. And that's a key part of the solution going forward, is that we have to be able to manage and communicate that, yet take that data, edge process it, and actually push it back into the relevant channels of information and control. So as you look at this, let me skip down this slide here, is that classical edge deployment, and we've talked about this in the last time, was that you have your ID management layer, which we typically your ADMS utility management, that would go then through your communications layers, and you know, it could be an edge network, it could be a HAN, it could be a WAN. It's really dependent on what the device is, but each one of these devices then communicate up into a communication layer, go to your ADMS layer, and go to utility management side. The latency on this actually, it's high. It's high because the communication protocols and the way that the interfaces are meant to react to this makes it a high latency response time. Now, there are pre-programmed sets points that we can do on edge grid devices. Yes, there are. There's actually different devices that we can pre-program, but I think it's a little bit more than that, right? I think that way that we have to really put this together is not only having your control preset. For example, let's say you have a cat bank. Your cat bank's turning on at temperature X and it turns off at temperature Y, right? Now those are pre-programmed and pre-processed edge commands, right? But as we make digital twins, as we get this data, that can be modified. That can be modified not only for your volt and energy consumption, but it can also be modified based on predictive analysis of the weather and actually optimize your grid. So when you look at that type of actual deployment, is that we're putting much more real-time management into the federated control structure. You know, I got a question from the last presentation about this, is like, who has underlying arching control of this? And it's, you know, it's always going to be the operator. It's always going to be the AMS side. It's always going to be on that. But however, when you do a grid edge deployed control, a lot of that real-time management, real-time management is going to happen on the edge, right? Those edge devices are now federated. What I mean by federated is that by having grid edge processing and having that actually in each device. So let's think about a distribution grid, right? For a typical, and let's transformer and substation. Let's say we have 6 feeders, and each feeder has 6 to 7 edge control devices with sensing, right? So we have approximately 36 sites that we're actually measuring from. Now, the interesting thing about this is each one of those distribution feeders could have a different load profile. They could have different customers. They could have different configurations of equipment, and it could also have different configurations of actually how it's actually operated. When we put this into a federated system, all 36 of those points are actually intelligent to each other, right? By being intelligent to each other and using a cloud analysis of this and cloud actual AI, we can actually do predictive optimization. We can actually do predictive maintenance, because now we have actual state changes of this. So when we put this into a federated edge, we can also tell it to behave differently based on what the situational is and based on previous learnings. So for example, you may be able to sectionalize on detection of a tap within wave cycles versus actually having to do a trip, reset, whatever the previous operation is. You can even do it within half wave cycles. That's where we're heading with this. And now with this new deployment edge, it gives us the capability not only for this higher resilience, now we can deploy this into actual energy savings. So we got another question. So is this phase before or after the actual installation of devices, i.e. reclosers, chip savers, SCADA switches, etc.? I think we have to be flexible on that. That's a really great question, whoever asked that, thank you. I think we really have to be flexible on the fact that it's gonna be in parallel, right? We all see grid upgrades where devices are going in, switching, sectionalizing, cap bank controllers, you know, different points of measurement. Those have to go in, and I think as we deploy this grid, it goes back to the future proofing and the flexibility. So devices that Micatu develops and the way that we actually deploy this is that if your device exists, great, we can tie that in. If it doesn't exist, well, you have a tie-in for it in the future. And I think that's the way we really have to handle this, because grid deployment timing, it's in various states for various different operations. So, but let's talk about what this data side looks like. I talked about this a little bit on my last presentation, but I want to talk about a little bit more. And what we see is 3 key indicators and how the actual low bandwidth, high value data, right? So this is actually a term that's going to become much, much more prevalent, is the fact that it's the value of the data versus the quantity of the data. While deep language learning models excel on data, but yet if we have more and more algorithms for actually cleansing of the data, and aggregation and integration is much more important. So really what we're seeing is that there's going to be, first off, data integration. This is tying back into all the equipment we spoke about earlier, where we identify entity identification. We also identify what it is, and also this ties back to what our digital twin is of actually the grid. The data cleansing component is now localized on the edge, right? Taking this vast amount of data, putting it into your servers or putting it into a cloud doesn't really make sense, especially when we're fully digitizing every point of our life, right? Is that we have to actually find out what the low value data is. There's many algorithms and methods, and we'll talk about that a little bit later, but also filling in the blanks. You could have high value data that was blank, right? And the last thing is abnormal or outliers of your current state. Now that data is incredibly valuable because not only does it tell you that potentially a state change for that data node, but also that state change can be indicative of the actual health or an actual state change of the device itself. So as we cleanse this, now we have high value data we can package up. And what we can do now is on the edge is we can do different levels of SKU processing. We can do different levels of actual core processing and put this into a standardized data format now, right? I know we have many communication protocols back and forth, but now we're talking packets of data that can be actually processed by AI into a federated system, right? And then we can actually do attribute construction, which this then ties back to our digital twins and actually the overall arching model that then drives a lot of this predictability and information back down. This can all go through the communication layer. And I think this is really how we're heading for what, the LBHV approach to this whole entire data can packet and valuation. So now that you have this, a lot of the different, there's a lot of different algorithms, and I want to touch on this because algorithms seem like it's this magic, right? And it seems like AI is this incredibly magic thing, but really there's 4 major different types of AI and machine learning, right? One of the most popular, and we're seeing quite a bit on the edge, is supervised learning. And I think this is going to be the predominant methodology, particularly on the edge, is that we have, there's 4 of the key ones for decision trees, K nearest neighbor, and this support vector machine classifier. These are all different types of algorithms that can actually take that data and use supervised learning sets. That's a huge challenge though. It's a huge challenge though, is because as we put devices in, you need to pre-train them. And there's a huge level of concern and security about data sets. And we saw this just the other, I saw this just the other day with Google, had a huge, massive amount of data leaks for these large language AI training models, and this data got leaked. That's a problem, and that's a problem because now we have to think about, to have this wonderful autonomous self-learning federated system, we need learning sets as we push towards a supervised learning, and that data is valuable. So how do we approach that problem? I don't think anyone has that particular answer on how do we train this and where do the data sets come from. But I think there's going to have to be a hybrid of genericized data, and it goes back to the point of standardization of data sets where there's actually the values intrinsic to the actual weighting to your model versus interpretive to the actual application and insightful to that. So we have to figure that out. That's a big problem. Now, the other question is could we go to other ones, unsupervised learning, correlation, dimensionality reduction? Yes, of course. There is a lot of opportunity for there, and I think as those algorithms capabilities where we don't have these large sets of data we have to train on, those are going to become more predominant, maybe to help solve some of these problems. So it's just some things to consider as we go further and further to the edges. What does our data look like? what's the value of the data, and how do we actually train on it? So let's we're gonna go forward to what are some of the federated edge benefits, right? So I'm really it's exciting to see this, and it's exciting to see this in the fact that we can really get to the grid where failure prediction is a common play and scheduled maintenance is going to happen. So for example, we have a piece of equipment that's putting a state that we're actually able to detect that it has a failure. Now with advanced AI, and this technology exists already, we just got to apply it to the grid. We can actually give you a prediction of how long that piece of equipment is going to work and how long till it absolutely fails, right? And algorithms for this have been around for quite a while, and particularly in the nuclear power plant industry, avionics, transportation, it's been there. We're moving towards that federated edge learning, is that as we get these data sets and the supervised learning, we can do predictability of failure, time to failure. Now we can do asset management, not only scheduled maintenance, but actually this ties back to part ordering, to actually making sure that you have in stock what you need to actually repair it. This, and also with the fault propagation, now that we have a stronger digital twin and we have stronger models, we can actually see what would the impact be, right? So we can actually do an impact analysis, for example, losing, let's say we lose 2 distribution lines. Let's say we had a major failure of a XYZ piece of equipment. What does that propagation of fault look like, right? During a wildfire, we lose, we have actually better vegetation management, but what happens during these kind of failure of a line and a line drop, and what would that failure look like, and what's the probability of how that's gonna propagate? So the other thing that's interesting too is we can get into not only fault propagation, but as we get more and more into fault prediction, is root cause recognition. We can get the RCAs in. We can actually tie this back into how we design the grid, but not only how we design the grid, but actually how is the equipment deployed and what is the work methods to actually deploy it. So a lot of the times, and this happens, it happens with everyone, is you have DOA equipment, right? You have equipment that fails prematurely. You have equipment that actually has a fault and it actually triggers another fault, right? And it keeps, or you have to take it out of service. So with this tied in with a federated edge, it gives us more of that insight. And the last thing that's really important is real-time fault detection. By being on the edge, we're talking response within wave cycles and corrective action within milliseconds. So this tied together is really putting together a more the resilient side of the power grid. So good. Excellent. So I got a question here. Businesses like Arcadia Power are basing the majority of their revenue model on data aggregation. How does this play into this particular method of data aggregation? Well, I'm not fully familiar exactly how they're doing that, but I think there's gonna be multiple players in the actual data aggregating on the edge, right? And the value proposition of high value data and the comms and communications behind that. You're going to see many companies such as, you know, big players, Oracle, the AWSs, the Googles, they're really into this part of the data grid because first off, it's big business, but other thing too, this is their wheelhouse, right? They have the tools, they have the methodologies to do this, and aggregation of data is now becoming a standard methodology as we go forward towards this. So awesome, excellent. So I got a really, this is a good question here. And by the way, everyone, thanks for asking the question. This is great. It's pretty exciting to see this. So how is data being protected from unauthorized access or us? And what mechanisms will be provided to allow customers to opt out of data collection and participation? Those are great questions. And I think those questions have to be answered on a multiple level, right? What I'm seeing in the industry is that most big data players are, all data is basically owned by the customer, by the end user, and that data is not accessible to the cloud providers. It's not accessible in any level to the actual end users. And I'm seeing that really become the policy, right? Every data is siloed, it's segregated, and it's it's treated as data. And this is particularly true when you look at the cloud service providers, is that they're selling the crunching of the data. The actual data is nebulous to them. But one of the challenges is going to be is we're going to need that data to actually program and build these advanced large language models. So there is no, I think, answer that's 100% solid on this. I think it's going to require participation and actual cleansing of the data and the data value, but also on a security basis. So, and what mechanisms to for consumers to opt out of data collection participation? You know, the interesting metric I saw last time, and I actually presented this, is most smart meters, I think the participation rate is less than 10% to start with. So I think the ability to opt in is kind of more of the challenge than opt out. Is the fact that majority of these actual meters are not sharing data, and if they are, the participation rate's so low. But I think it goes to most other end user licensing, is that you want advanced features, you want to have you know, control your bill, sell back, have a bidirectional relationship with your utility. It's going to take some participation at different levels, right? So good questions. So with that said, I'm going to talk a little bit about where can sensing be deployed and some of the solutions that we've done and for data collection, because one of the things that I want to just kind of touch on different types of interactions and how do you get the retrofitability. You know, one thing that sensing underground is becoming more important, particularly in vaults and vault applications. So you can see that one sensor deployment that we've done, and part of this is how do we tie into these existing underground infrastructure, you know, dead brick elbows, the options there. And one of the things that's challenging about this is the environment. So you got to make sure you're non-conductive and you're actually extensively waterproof. So that's one solution we've put through. Another exciting one is that outside of solar plants, it's very important to actually monitor the production, not only if you're the utility operator, but also if you're the solar plant or energy generation provider. So it's important to do that. Some of the solutions we provide are line hanging sensors, actually can be deployed rapidly, can get tied into your ADMS through SCADA system, but also starts as a data collector on the edge. So excellent. And then last thing too is that substation monitoring is a really big market also. So we, you know, it's not only the monitoring of the distribution feeder lines and individual points along the line, it's actually on the utility, on the actual substation side off the transformer. So, you know, we have many technologies that go there also. And what we're seeing is that there is a growing demand to actually know at the beginning and end of distribution lines to actually be able to get that volt var and that end of line voltage is correct, because sometimes there's absolutely no insight at the end of the line. So some of the applications we did, but I think that kind of wraps it up for today. Had a really great time talking about this today, and if you guys have any questions and further ones, let's go through them, because I think we have what do we have in like another 5 to 10 minutes here. So I got another question. Question is, do you ever foresee over dependence on digitalization than human involvement as we progress towards carbon neutrality? Yeah, I mean, that's a deep question. That's a very deep question. I'm not sure how we can do it without having the operational insight, right? To me, the challenge is that we're no longer a linear topology. What worked back in the early days of electrification, always going back to when Tesla turned on with Westinghouse at Niagara, right, is that we had a power plant, we had transmission, we had a substation, and then we had your house, school, factory. It was always at the end. That's no longer the case. So is digitalization is a necessary evil? Absolutely. Now, I think it has to have strong controls and around protecting privacy and also protecting the value of data, right? The data we provide is valuable. So I think that's going to change over time. So it's going to be evolved and it's going to be evolving. I don't think there's a singular answer now because it's such a complex question, right, to answer, but it's a necessary evil. So great. It looks like you guys got the email link to my last presentation, really started to talk about the top of this, and it's been exciting about going more and more in depth about this and talking more about the algorithms and the data and where we're heading. It's exciting times. We're going through a fundamental transformation of the utility, and I think I couldn't be more excited to face some of these challenges, because it's important not only for our children, but our children's children, really, to get through some of these challenges and help decarbonize, because we all know that whatever our stance are, it's the right way to go. So I got another good question here. Any thoughts on the cost with respect to device costs in terms of percentage for estimation purposes? Yeah, I think really what we're looking at in some of the models that we have, and if you guys have want to reach out to me, I'm sure we can put our contact information. Please feel free to reach out. But I've developed a really in-depth ROI model that actually can calculate what does an edge device ROI look like in percentage of savings, of operational efficiencies, and asset management, and outages, and SAIDI and SAFE, right? What does that look like? And typically, return is almost somewhere around 500% on average. I know it sounds incredibly large. I know it sounds like, oh yeah, sure. I'd love to, and maybe we talk about this in another webinar, is what's the value proposition of edge control and real-time data management and digitalization. But the actual, as a percentage, is the actual equipment itself pays for itself typically within 2 to 3 years ROI, if not faster, depending on the application you're using it for. So it's highly application dependent, but the insights to operational efficiency, asset management is rather large. So cool. So I think that's, we're at 11:45 here, and let's see if you guys have any last questions for us today.
So far, that's the last one on the floor. We can give folks just a minute in case anyone's typing. We do have some comments. Michael, great presentation.
Oh, thank you.
Looks like folks
really love doing this. And I know I like to nerd out with the data side, but it's exciting. It's very exciting where we can go. It's very exciting, the opportunity we have, the responsibility we've taken on to change this grid, right? So, it's good. So I got another person. So with 5 O's, if the ROI is so good and the payback's under 5 years, why don't the utilities self-fund instead of federal dollars? Well, good question. The federal dollars being thrown across the board. I mean, I think I've seen a combination where utilities are self-funding through mandates, but also the federal dollars are there. I mean, it's no brainer to use that. And also the incentivizes for sometimes when budgets are through, either they don't have a rate case, they don't have the ancillary budget. I think this is developing, but the use of this of the budgets is great. So awesome. So yeah, questions, email me, marketing@micatu.com. And I really appreciate the opportunity to get to talk to everyone today. And please join again next time we talk. So thank you.
Thanks, Michael. And you did a fantastic job. And for the audience, we want to let you know that there will be a survey popping up that you can additionally add comments and feedback for us. You can email us as well. And we look forward to reading those and reaching back to you. Thank you all for attending. We hope you've enjoyed today's presentation. And this does conclude today's talk. Have a great one, everyone.
We'll see you.